So welcome everybody. We're very pleased to have John Shelf with us today. John is a collaborator at Lawrence Berkeley National Lab, where he's the department head of the Computing and Data Sciences department. And in a previous life, he helped build a system called Cactus, which is one of these frameworks that we're going to be talking about that would let people doing general relativity easily write large, high-performance simulations. And of course, now it's used for lots of other things, and there are lots of other frameworks to do that too. So,
all right. Thanks. So we're going to talk about frameworks for multiphysics HPC apps. So I just wanted to preface this with, frameworks actually appear in business applications too. If you look in your Apple, it's got a whole framework subdirectory. The key is that the same kind of software engineering discipline needs to come to HPC because the complexity of our applications for scientific computing have grown enormously over the past decade. And big science in the leading edge HPC systems is multidisciplinary, multi-institutional, multinational efforts. We're not just talking about particle accelerators and tokamaks where you have hundreds of authors in a paper. This is happening with HPC codes. And so, science performed on supercomputers is looking more and more like the kind of science that we used to do with atom smashers. And advanced parallel languages, they are absolutely necessary for a productive programming environment. They're necessary, but they're not sufficient. There's another layer that we need to bring to bear, a higher order organizing construct to bring together teams of programmers so that they can work productively together in very large multiphysics code bases. So languages, and frameworks need to work together to create a complete solution. And one of my hobby horses in the language space is we should be thinking about language extensions that don't just express something about parallelism, but also enable the kind of modularity and collaboration that we have in the programming model space. So, for example, this was a recent Gordon Bell. Well, it's not recent anymore, I guess. But this one was kind of a wake-up call. If you look at the number of co-authors in this paper, and this was intense. This is. It used to be that you only saw this number of co-authors if you they discovered a new particle at CERN, and we're seeing these kinds of large multidisciplinary code bases in order to take it to the next level in terms of physics and fidelity for HPC codes. So the code that I worked on was a multinational effort to detect gravitational waves, and in order to design a detector to find gravitational waves, we need to know what they would look like were they there to be found. And so they have these multi-billion-dollar detectors being built where they have these long arms with a laser shining down the column, and it detects perturbations in the order of 1/10 of a hydrogen nucleus, movement in the size of the arms that are caused by gravitational waves propagating through. And they believe that these, the observable gravitational waves would come from the inspiraling merger of two neutron stars or two black holes. And they estimate there's about 200 of these events per year. They're very far away, of course, but you can take, without a computer, you can actually do kind of an analytic solution for the kind of gravitational radiation that you'd expect as these things start spiraling closer to each other. But the place where it's all very interesting and where you could really detect something is when they merge. And this is where everything becomes extremely nonlinear and unpredictable. And they'd like to find out, using computer simulation, model something that can't be done with straight mathematics. Einstein's equations only tell you what things look like over here and what they look like over here. For this area in between, we have to do computational models that evolve Einstein's equations forwards from first principles as a PDE solution. So that required a team of about 20 programmers, 7 or 8 years in order to put together a code that could really do that and matched up with other experimental results. So these are some of the grand challenges that kind of led up to having a fully capable code. I mean, the first one that I was actually involved with was the NSF Black Hole Grand Challenge. That was 8 institutions for 5 years. That was like 93 to 98, I guess. And so that we did the first simulation in 2D of 2 black holes merging. And this also led into the NASA Neutron Star Grand Challenge, where we had to add, in addition to Einstein's equation, had to add fluid dynamics. Then the next, and this is after I had left the team, they continued with gamma ray bursts from core collapse supernova. And so you can see the growth here. This is 10 institutions over 10 years, 8 different countries represented, and multiple disciplines. So you have now general relativity, which was what we were doing back in the 90s, plus hydro, plus chemistry, plus radiation transport, and analytic topology in order to understand what was happening where these guys were merging. These software teams, there's no way that the hydro guy knows what the analytic topologist is thinking and vice versa. You need to have some way to bring these disparate teams together and organize your geographically distributed code team. So, yeah.
And there were millions of lines of code written? Is that what that set up?
Oh, yeah. We have a code base that checked in that's on the order of 12 million lines of code now. But that includes all of the different things that Cactus can do. So any given simulation probably involves, maybe 3 million lines of that 12 million. But there's a lot of physics modules. And so you definitely need a higher order. When we talk about kernels and optimizing kernels, you know this. So the key here is community codes and frameworks. What we're really doing here is hiding this complexity with good software engineering practices. But it also, when we talk about the dwarfs or motifs, there's a certain correspondence of that higher level organizing principle for algorithms that you use you build your framework around that dwarf or motif or whatever that you're targeting. The key thing with the frameworks is that they clearly separate the roles and responsibilities of your expert programmers from your domain scientists. In Parlab they talk about the productivity layer versus a performance layer. I actually have a 3-layer cake that I'll introduce to you a little later because we have numerical analysts fit in here somewhere. The other is defining, the framework is also kind of your definition of a social contract between your expert programmers and your domain scientists. There were constant battles of Fortran because it's nice to have an array as a first-class 3D, object, but then you'd have all the computer scientists come in and do template metaprogramming and inflict that upon these physicists. And defining the social contract says, where do we cross the boundary between the kind of stuff that the expert coders need to twiddle with and the kind of programming environment that you want to present to a physicist who doesn't know the inner workings of your supercomputer. It facilitates also an engineering style and discipline to your programming to ensure correctness. It would be great, there's bondage and discipline languages that can enforce, strictly enforce a style and discipline to ensure correctness, but software engineering is more about more of a handshake contract or maybe a set of rules that you agree to abide by even though the language might not necessarily enforce it for you. You may bake some things into your framework to check for correctness and ensure discipline, but it just says that your programming interfaces, your data structures will all follow a certain set of rules so that everybody can read everybody else's code more easily. It also hides very complicated domain-specific parallel abstractions, and I'll be talking about that when I review other frameworks too, to show how that plays out. Domain-specific parallel abstracts from your scientists and users, so that the performance people can mess with the parallelism, and the scientists are presented with the simplest possible environment to present their algorithm, and it allows the scientist to code to a nominally serial plugin type interface, and then the fancy stuff is invoked by a parallel driver that manages data layout, communication, parallelism, all of that stuff behind the back of the person who is writing the scientific plugins. So, I already covered this. There's a number of frameworks that we can talk about. There's Chombo. Cactus is the one I worked on. Chombo is one that's up the hill. Phil Collella's group. Brian von Strahlen proctored this class last year, I guess. So there's a lot of slides from him. There's UPIC. I was telling you that, pointed out earlier, there's a certain correspondence. So frameworks tend to glom around those dwarves, the 7 dwarves that Phil talked about. UPIC is a particle framework. It's used to is a toolkit for creating particle and cell codes. Sierra is a finite elements toolkit for doing finite element structures codes. Chombo and Cactus was invented for PDEs and block structured grids, and Chombo is targeted at AMR, adaptive mesh refinement type applications. Cactus can do that too, but Chombo has a longer history with that than Cactus. So the key is that, in order to enable these features that I talked about in the previous slide, I'm going to point using. In order to talk about these features that I talked about in the previous slide, something that was curious to me is that independently developed frameworks, UPIC, Sierra, Cactus, Chombo, all have arrived at the same programming, software engineering paradigm to enable scalable parallel programming in discipline, and that is to create a kind of a plug-in interface where you basically, in a classic HPC code, you control main, and you go into the, you initialize all your variables, and then you start going into a loop where you call your solver subroutines in order in this main event loop. What the plugin says is you, the physicist, needs to relinquish control of main, and you instead code to a plugin interface that will be invoked when your framework decides it's time to invoke it. And that module that you write, and this is common across all the frameworks that I've seen thus far, it must be stateless. It means it doesn't carry any internal state between each invocation. All state is externalized. This allows you, and it operates only, when you do invoke the module, it only operates in the data that it was given through the calling interface. And that means that it has no side effects. I/O modules implicitly have side effects, so we'll set those aside. But if you program to a no side effects to this discipline, it provides the maximum freedom for doing this.
So, if you give up main, how do you use more than one of these modules that both require you to give up main?
So we. I guess I'll talk about this in the Cactus thing. Instead of saying, that having just kind of a list of calling the modules in order and having it be imperative. The issue with our current programming interfaces is that the compiler, when you present things in program order, the compiler has to do a lot of theorem proving to know that it's legal to do them in a different order than you presented them. And it may actually be better to execute these things in a different order than you presented it. So there are two things. One is if you program to this discipline here, you actually have coarse-grained data flow semantics. That means now I know what all of my side effects and dependencies are between these modules, and I can decide that gives the freedom to the framework to reorder the computations. And also it gives the framework the freedom to completely change the data layout. And the physicist wouldn't have to rewrite their module to deal with the fact that the framework decided that a different data layout was better on a parallel machine. And lastly, in Cactus, we actually had kind of a lazy man's semantics. When you wanted to do a multiphysics simulation, you'd say include hydro, include GR, and you might have some sub-modules. And then you'd say the elliptic solve has to occur before the hydro solve. And it would figure out a data flow, a DAG, a data flow graph from that information as well. So, so it allows you to have instead of an imperative syntax or semantics for declaring your program execution, you switch to a declarative semantics, and that gives more freedom for reorganizing the order of computation. So, frameworks, you can think of that as a driver. Well, that gets to what the next big bullet is here. The framework can be thought of as a driver for coarse-grained functional style of programming or coarse-grained data flow. Fine-grained data flow wasn't such a good idea. Coarse-grained data flow, though, there's a lot to like about it, especially since the computation is applied to the data where it resides, which means that, you want to minimize data movement, so you can apply computation where the data sits. And so that means the framework gets to decide what the optimal layout for the data is, and then apply computation to it. So it's just like classic static data flow, except coarse-grained objects, and inside of that object, you don't have to use Haskell or Lisp as your base programming language. You have Fortran or C or Java, and you can program using your familiar imperative programming style inside of that module. But outside of that module, it's a coarse-grained data flow, meaning that you have to adhere to functional semantics. And that also gives you broad flexibility to schedule this as a directed data flow graph. So the other part of this is that when we originally started Cactus, it was actually to fix long simmering battles amongst our computer scientists and physicists. There are two things that were going on. Number one, the classic argument of C++ versus Fortran. Oh, won't you use a modern language? And, well, we will when your language doesn't have sucky performance, or, the template metaprogramming doesn't fix that. So no more arguments of C++ versus Fortran. With this modular architecture for the system, it makes unit testing much easier. What we had with our original code base, even with revision control, somebody would change something, and somebody else would check out the latest copy of the code, run a simulation, and the answer would be different. And they'd just freak out, and there would be finger pointing, name calling, and you'd have to fence people off and get them to calm down to identify where the error crept into the code or why it had changed the answer. Well, unit testing is the first thing, but unit testing on a huge monolithic code is a pain in the butt. By creating these modules, we could actually automate the unit testing process, where your data would flow through these modules. You do snapshots of the data as it came in and came out of the module, and then every time you did a check-in, it would rerun that module and find out if the answer was the same, or do a battery of tests, and all that could be automated. So much better thing. The other thing that they had is if a computer scientist decided to do something experimental, you change the code and then you give it back to the physicist, and they'd never touch the code again, because they were sure that if a computer scientist touched the code, that it was tainted forever and could never be trusted again. This modularity enabled the computer scientists to do really cool stuff for the physicists that they eventually could trust. It also enables, multidisciplinary domain scientist computer jock collaboration, and we'll talk about, we had SMS messaging service, and we even have a Twitter feed, built into the general relativity code now. So you can do that kind of stuff if you have a modular code.
Hopefully the Twitter feed isn't in the inner loop.
Yeah, well, things of that sort have happened, but all right. So so these advanced computer science features, like Twitter feeds, built-in parallel visualization software, things like that. All you have to do to make it accessible to an application scientist, say, I want the visualization plugin, and then all those features are in there, and these modules are introspective, meaning that the module that you wrote to do the viz doesn't have to know anything about general relativity. It's able, when it plugs into the framework, it queries the framework and it gets an inventory of all the data arrays that could be presented, and then you get to choose what you want to visualize. So the introspection is another feature of these kind of software frameworks, and it's also trivially unit testable, so that you don't have to worry about fancy modules damaging your physics. And then lastly, it enables sharing of physics modules amongst the computational scientists. So we, for example, the Hydro module that we used for the neutron stars was actually developed at Valencia, University of Valencia in Italy. It got packaged up as a Thorn, and then suddenly everybody who was using Cactus code had access to a first-rate Hydro solver. And they didn't necessarily have to be experts in Hydro to be able to utilize it. So key, though, is being able to organize large teams of programmers along their lines of expertise. So this is the development expertise diagram I was telling you about. So in Parlab, there's performance programmers and there's productivity programmers. We organize ours along the lines, this is a Microsoft taxonomy. So Einstein is an expert in it. Elvis means can dance, but not necessarily an expert. I'm supposed to be using the pointer. So Elvis can dance, and Mort doesn't know shit from Shinola. So the Morts, so if you think about your application scientists, they very much understand general relativity, the physics of colliding black holes, and they're assembling together these simulations with lots of different solvers and stuff in it. Their coding expertise is they know how to code. They know Fortran and stuff, but they're not experts in coding, and they don't know. They have all sorts of really interesting and really incorrect theories about how computers work, and you don't want them really messing with the guts of the code. You have this intermediate level, which is the people who are writing the solvers. They have a very strong background in applied math and also writing high performance code. They're not the ultimate performance people in terms of hardware expertise. There's people who really love optimizing communication libraries. They're down here at the driver layer, but these folks don't really, they can read the equations that they have in general relativity, but they cannot, they're not going to be writing GR codes. They're going to be writing very fast elliptic solvers or hydro solvers, for-said codes. And then you got the driver people, and these are folks that really love template metaprogramming or assembly language and love messing around with communication libraries and parallelism constructs and stuff like that. And they're at the lowest layer. And in the case of Cactus, we have specific examples here where conceptually these guys want to do neutron star simulation. They string together Hydro, GR, and AMR. They have specific Hydro and AMR drivers that they string together, and the framework just makes all these plugins happen. You just give it a list of the plugins, and it figures out how to instantiate a code from that. The solver writer will focus on an elliptic solver, and we have multiple implementations of elliptic solvers. Some are better than others depending on which machine and which circumstance. So we have everything from John Towns's custom BiCG stab that he wrote for the CM5 to full PETSI elliptic solver package. All of these, though, have exactly the same interface and are interchangeable when you plug them into the framework after we wrap them for the framework. And at the driver layer, we have parallel boundary exchange for block structured grids. And so that's the low-level communication data layout choices. And there, again, those are all plugins too. So our modus operandi for parallelism, we have a carpet driver, Samurai AMR, Grace, Manish Parishar's AMR driver, Pug, which was our original MPI non-AMR driver, and Schmug, which was our SMP driver. When you plug in a different driver to implement your scheme for parallelism, none of these modules have to know about it. So the framework is written in such a way that I can choose a model for computation at the bottom layer here, and I can mix and match. I can decide I'm going to use Samurai instead of Carpet. None of these modules change. None of these modules change. At this level, I can change my elliptic solver, but the guy up here only knows that he's using an elliptic solver and doesn't, if you switch out for a different elliptic solver, that wouldn't affect the code up at this level. So there's isolation of these three levels of concern. So there's a question about what's the difference between a library and a framework. Well, a library is a user program invokes the library. So this is imperative execution. You invoke it through a subroutine call. And often libraries are designed to that you present to the library a particular data layout, or the library might define for you a data layout that you have to adhere to, but there's no runtime freedom for the compiler or the system or the runtime to decide to reorganize the data layout if conditions require it under that circumstance. And so because you own main, and also you're stuck with the base language, the base language semantics, you have very limited degrees of freedom to reorganize stuff. You can do it, but it's kind of hard. With the framework, you don't own main. The framework invokes the user plugin, so you have a declarative execution model. You only operate on the data that you're given, and that functional semantics provides a lot more scheduling freedom. And this is another view of the same thing, which was Kaushik Sen said that these things, though, can be embedded recursively, where you can have serial code invoking a parallel library, or you could have a parallel pattern with serial plugins, which is what the framework is doing, or you could have any composition or recursive composition of these things. So it isn't an either-or proposition here. It's really a question of who owns main, who has the control. So this is from a DARPA project that we had, and this was a kind of a taxonomy of frameworks. So like I said, frameworks aren't something that we invented or anything here. There's a lot of people have frameworks, and we did identify that there are many different levels of coupling for frameworks, from fully coupled to loosely coupled. So typically physicists in old school would each implement their own physics as a completely separate program. So you'd have an electromagnetics package and acoustics and fluids, and these things were just standalone. They do one-trick ponies. So there's a lot of the engineering firms like Abacus and what's NHK? Nastran. They do coupling. They do multiphysics coupling, but they do it by having separate programs, completely separate programs, and they write out a file that gets read in by another package, and it cycles around by sharing data by writing and reading files, which is kind of loopy, but it works. And what we're talking about here are a common infrastructure where you identify the strict data structures, software engineering practices, so that we can actually do full coupling between these and actually directly share and have the common infrastructure manage data layout and parallelism for you. So integration is invasive. You have to give something up in order to gain this collaborative type environment. So the observation here with the domain-specific frameworks are that they enforce, and also domain-specific languages kind of fall in this category too, but they enforce coding conventions for big software teams. They encapsulate a domain-specific idiom for parallelism, whether it be for PDEs and block-structured grids or dense linear algebra or particles. They create familiar semantics for domain experts. So the framework is usually built around a target problem space, and that enables you to make that upper layer of that three-layer cake be as close to the problem domain as possible without being too restrictive. Oh. Yeah?
I was wondering, I'll let you choose the metric for how to answer this question, just sort of based on experience, but I'm wondering how much performance difference do you get in practice when you decide we're going to make things a little more tightly coupled, we're going to share data structures, we're going to keep it in memory, we're not going to write to files, and so on?
Well, it's huge compared to writing to files. The writing to files is so ridiculous that it's I mean, when I first heard that people were still doing that, I was shocked, and people are still doing that. So if you talk to Procter & Gamble, when they want to do like Pampers diapers, they're worried about the crinkly acoustics, but they're also worried about it after the baby pees in it. So they're coupling acoustics with structural mechanics, with fluid dynamics, and it's just craziness. That's how it works. So there's a huge performance gain in switching to this approach.
Now, just to follow up on that a little
Yeah.
bit, when you say writing to files, you mean actually like writing out to an on-disk file system,
It's
or
as
are they doing
crazy
in-memory
as
file
you
systems?
could imagine. So it's, yes, so they got their big optimization. Their huge breakthrough was at about 8 years ago. They hijacked the POSIX I/O so it would write to a memory buffer instead of to a file, but it thought it was writing to a file. And that was big, but it's still kind of crazy. Yeah. So so they do have them writing to virtual files, but it's much better. I think that going the extra step here, when we actually got a better separation between the driver layer and what the physicists were doing at the upper layer, there was always an issue with it. Really restricted what we could do as computer scientists to optimize the code when they had control of main and they do all sorts of crazy stuff that you didn't expect them to.
And this writing of files had to happen every time step?
Yes, every time step. And sometimes they could cheat by saying, well, maybe if I skipped a time step or two, but that was just in the margins. I would say that the Fusion simulation project is still talking about that kind of thing, which just makes me wring my hands. So, I participated in those meetings for a while until I couldn't stand it anymore. This is being recorded, isn't it? Okay. Well, yeah, so, common design principles, for frameworks, and we had a number of meetings. So we started having meetings at the SIAM, CSE conferences, so we regularly get the frameworks people get together. We've had frameworks was actually a conference series that we had. We had also the DARPA meeting at Ogden. Everybody, we all disagreed on what the right thing was to do with the details, but everybody came up with exactly the same 3 principles for how do you design a parallel software framework. And that's give up main, stateless plugins, and bounded side effects. So let's talk about Cactus. And so I'm going to go through 3 examples here. So I have Cactus, Chombo, and Petsy queued up. And I think this time around, I will probably skip through a lot of the Chombo stuff since Brian isn't here to correct me, and we'll mostly focus on Cactus and Petsy. So Cactus was as I said, it was for HPC code development. We started the project in 1997. So. Guess it's about 16 years old now. I think we had a birthday party for it. And a lot of these slides are as old as the project. So I was in Cactus 1, 2, and 3. They have Cactus 4 and 5 that I had no hand in. So the Cactus team lives on, even though I've long since left general relativity. And they have a really strong group of developers right now that keep the thing going. So that's the other thing, is that it has life beyond the original writing team. Is it this language or just structured programming? Well, people always ask, what about a programming language? What about structured programming? No, you need both. It isn't an either-or question. You need both. So this is the user community, and it's actually we started at NCSA at University of Illinois. We moved to the Max Planck Institute in Potsdam, Germany, or Albert Einstein Institute, and so there's still a team there. And then that group moved to LSU in the U.S. Because the LIGO is there, and Ed Seidel, who leads the group, got a huge CS program started there. So the center of development these days is at LSU, and so if you go to Cactus toolkit, cactuscode.org, it's a LSU website. We still have the AEI, the Albert Einstein Institute developers around, but we have people, pretty much every general relativity group in the US and Europe has Cactus as part of the tools in their toolkit. For our astrophysics, for the magneto, hydrodynamics, and radiation transport, Zeus MP, which was developed by Mike Norman, originally when he was at Lanel and his team, so all the MHD and radiation transport is the Zeus MP module. There's computational fluid dynamics from the Korean Institute for Technology. DLR, which is a German concern, and I forgot to put Valencia in there. And then we have chemistry package from University of Oklahoma and bioinformatics package from University of Chicago. So, Cactus features a scalable model for computation. We've won 2 Gordon Bell Awards, which I didn't think was allowed. Oh no, they were finalists twice, but they won once. And so it scales to the largest machines on the planet. And yet it hides, and there's a lot of other frameworks. There was a recent one I saw called Neuron, which is hides the idiom for parallelism for parallel neurodynamic stuff, which I thought was cool. That was a long time ago, though. It has a build system that eliminates the need for make files. So all you have to do is say, these are the files that you have a disciplined way of adding new modules to the module repository. So you create a subdirectory and you put your modules in there. But then you just give it the list of files and also where you invoke that module. In a text file called a CCL, a Cactus configuration language file, and it figures out how to generate the build files for any platform. So whether you're building on a laptop or the biggest supercomputer or the biggest, weirdest supercomputer, it figures it all out for you. All you have to do is type make and it figures it out. It has a modular application composition system that enables you to maintain kind of a database or an archive of all the different modules available.
So the point of that one is you can design and develop on your laptop, and when you're ready to go parallel, you don't have to change much.
That's right. We love developing our codes on our laptops, and the idea that you would only have a programming environment that's available on the big HPC system is just a non-starter. So, you do a lot of testing and development on your laptop. You might run bigger on your desktop. It'll run on a commodity cluster, and it will, in the case of the Lanel machine, it'll run on weird things like Roadrunner. And when we started it, there was a lot larger gap between laptop and the weirdest thing the supercomputing guys could throw at us than there is today. So it enables uniform, so you don't have to have a bunch of pound if-defs in your code. A uniform programming environment across all those things. It has a modular application composition system. You just give the list of physics that you need, and it'll figure out how to string those thorns together for you. And it has language neutrality in that it'll auto-wrap any of these languages. And it has, when you follow its discipline for describing data structures, it'll handle the wrapping of the data structures that are passed in. So you could have modules that are written in C++ working side by side with classic Fortran 77. And there's a particular discipline for how it'll pick apart a complex data structure that you have in C, C++, and make it accessible within Fortran. Yeah.
And V&V stands for?
Verification and validation. So where did I have that? V&V, unit testing and V&V. So the modular composition system enables us to automatically generate unit tests. So when you define a module and you've decided that you've got it to the level of correctness, then you can press kind of the record button that says, this is what when I present this input, this is what the output should look like. And if that continues to match, then this module is still valid. You can When you decide to then start optimizing code or changing things, then you can just say, unit test my module again for me, just to make sure that I didn't introduce problems or strangeness in the numerics. And it'll pick up that recording and tell you if something differs. Sometimes it's just transposition of an add and a multiply or something stupid like that. Other times it's something more serious. But it was huge to be able to isolate errors, to be able to automate that process. And also, we could separately analyze the hydro from the general relativity components for multiphysics app too. So we'd separately validate those things, and then we try to do cross-validation with the things plugged together. So let's see here, what else we got? We automatically generate bindings and get rid of religious battles. So in terms of terminology in Cactus, it was Paul Walker actually started the whole Cactus kick. And Paul's original proposal for Cactus was to solve thorny problems in general relativity. It's kind of a weak pun, but and so he proposed that we would generate this common infrastructure, which was the flesh of the cactus, and that we would plug thorns into the cactus, and we'd build codes that way. And after much argument, another year and a half of argumentation, we agreed on the interfaces. And that's the first lesson, is writing the framework isn't the time-consuming thing. Getting a whole bunch of applied mathematicians and physicists and computer scientists to agree to any common interface is actually the hardest thing to do. And so, in a thorn, this module that I was talking about, you have particular interface types, for describing arrays or parameters for your simulation code that are rigorously defined. But when we describe that we're going to have one of them, it's an abstract type, so it's a distributed array. It isn't like struct array with all sorts of little parameters in it. You say, this is the distributed array, don't look inside, please. And you have a certain set of actions you can apply to the distributed array. You have a schedule, which is the constraint-based scheduler for DAG scheduling. And then you have your parameters or first-class objects, because to run simulation codes, you usually have a parameter file that you need to parse to set the parameters for the free parameters for your simulation. When I first came in the team, they had a Fortran. Somebody wrote in a parser in Fortran for the parameter file, and all of the digits had to be in column 40 or else. And we had lots of simulations fail when you accidentally put a tab in instead of spaces, for example. So the driver, it separates your implementation for your idiom of parallelism from the implementation of the solver. So you define your solver as a module, but you also define the thing that decides how to lay out data in parallel in the machine and do the scheduling is specified completely independently and doesn't require changes for the definition module for the solver. That's all the magic of functional semantics enable us to do that. And the driver handles your communication, abstractions, and scheduling and data layout. And then the flesh. The flesh used to be pretty large, but over time, as we've modularized more and more, the flesh is now very thin. They should probably call it rows, except some compiler dude took that name already. But the flesh is just the thing that generates the make files automatically and does the setup in the scripts to make it run. And it's really just assembles things based on the constraints described in that Cactus configuration language. So our idiom for parallelism in Cactus is really just halo exchange for block structured grids to first order. The very first one, you basically tile. You have a big 3D logical array, but you tile it, and it handles the boundary exchange in those grids. The key thing is that those solvers, those stateless solvers that you invoke, they're handed a grid patch and they're told what the size of that grid patch is, and they say, just do your thing in this piece of the grid. You don't need to know anything else about what everybody else is doing. Just do your thing in this piece of the grid. And I'll handle the communication automatically for you. If a variable is written to it, it knows that it needs to update that variable in the next iteration. And because I said that it was a distributed array, and that's again rigorously defining what the semantics are of your objects is important. But we also found that after we went from this to AMR, where you don't just have halo exchange, you also have prolongation and restriction operations between coarse and fine grids, that the solvers didn't have to change for that either because it was stateless. We could smuggle in all of the AMR operations as a separate, driver Thorn, and you were still invoking the solver on its local patch, and it just did its thing in the local patch, and we didn't have to change any code inside of most of our solvers to make it go from unigrid to AMR, which is kind of cool. And we have several different implementations of AMR framework by people who chose not to, after agreeing on everything, we chose to disagree again. So there's a lot of frameworks, and so these are just pointers to you to other frameworks that are of interest. There's Neuron, which is a parallel neurodynamic simulator based on the Genesis Neurodyne program. Sierra is a finite element structural mechanics. UPIC and also TechX creates a PIC code, yeah.
So your last slide was the structured grid dwarf, basically, and are there any other of the dwarfs that are used in Cactus?
Yeah, so there was somebody's been working on a finite elements dwarf, and I don't know where that's at, and they definitely have particles in here because there's a strong interaction between particle and cell codes and field solvers like we have with the PDEs and block structured grids. I created a isosurface Thorn, which actually enables us to embed. So we have embedded geometry is another thing that we have, which I'm not sure how you'd categorize that in terms of the Thorns, but you might put it like the finite elements Thorn. There are two uses for it. One is for parallel visualization, so I used it for isosurfaces. The other is that the singularity at the center of a black hole is not something that you want to expose. So you have interior embedded boundary conditions based on the event horizon of the black hole, and so that very same set of semantics we created for the isosurfacer was also used for embedded boundaries and excision of the throat of the black hole. Hey.
Is the bioinformatics Thorn?
Oh yeah, and bioinformatics. But bioinformatics, that was the embarrassingly parallel, one that we never really talk about. So. The bioinformatics was that we baked into, we had a lot of parameter studies with, with any of these physics things. And you'd want to fire off a whole bunch of runs that studied a particular parameter space and then summarize the differences or the outcomes. So we developed a driver for doing these distributed large arrays of simulations and summarizing the data. And one of the bioinformatics guys said, hey, we kind of need that too. And so they did a parallel blast implementation like in 99 or 2000. And then they started using it for Smith-Waterman and all sorts of bioinformatics stuff. And that's Dave Angulo at University of Chicago. And you'd have to look up Angulo and Cactus bioinformatics, and you can find out more. But all I remember was suddenly we were doing blast on big machines, and I have a slide for that actually. All right, so correctness testing. I already said all this stuff all over again. So let's talk about how Cactus works. So this is a scalar wave equation. 3D. You basically drop a stone in water and watch the waves propagate away from it. And that's what it looks like before you discretize the equation. It's got spatial derivative components and a time derivative component, and it evolves forward in time. And do I have an animation? No. Okay. The way that you, though, want to solve this in a supercomputer is you have to take that continuous, representation. You got to discretize it, and that's the finite difference. Is that I have, neighboring grid points, and my spatial derivative and my time derivatives are based on the delta spacing of the grid, so measuring the difference in that, and also taking into account the time step size. And so this is the discretized version of that. And by the way, we're not even in the Cactus yet. This is just how somebody's going to write a piece of code to do PDEs and block structured grids. So we take that discretized equation, and we need to also have have it evolve on a multi-dimensional grid. So this is a 2D grid, but you'd want to do it on a 3D grid, and you have to apply boundary conditions and all sorts of fun stuff. And your main parameters for this code are your grid spacing, your delta t, and the spatial difference. This is such a simple problem. There really is an analytic solution to it. So there's no point in really using a supercomputer to solve this. However, what you do is you test out your PDE solver with something that has an analytic solution. So then I can do sort of more complicated things, like if I dropped my coffee cup into the water, and now I have something that I won't have an analytic solution for that this same framework, once I validate it, is able to model. So you use supercomputers to model things that have have a difficult analytic solution. So this is what my code would look like. So after I've done all this stuff that I talked about here, is I have to set up all those parameters that I was talking about. I have to set up my coordinate system and my grid. I have to include some crap over here. And then this is my main evolution loop over here. I keep on forgetting. All right, that's my main evolution loop here. And then I have to write some output. I have to F open a bunch of files, and then I have to shut everything down. So that's just doing the wave equation 3D. That simple little equation, I got all this stuff I have to write.
And that's one time step.
Well, let's see here. Do one. Oh yeah, it is one time step. I neglected to do more than one time step. So there should be an outer loop, so you can do more than one time step. Or I would have a do loop that is outside of this open output files thing.
Maybe the do loop is down. The outer loop is down there.
Oh yeah, there it is.
Okay.
Call evolve. Oh, this is evolve up here. I'm sorry. Yeah. Okay. So this would be like in a package in a subroutine. It would be evolve, and then I do iteration 1 to nt. I call evolve, and I also call write my output files when it makes sense. Oh yeah, this was initializing the data. All right, I'm messed up, but that's all right. You get the general idea. When I output stuff, I'll get this, the wave equation. Great. Works serially, and it's about 300 lines of code. So now if I want to make this a Cactus module, I just boxed the wrong thing, but that's okay. The general idea is that the Cactus infrastructure manages the setup of your grids, the management of the parameters, and even the I/O and the output required. So all the physicist has to do is create a plugin that defines what happens for the wave equation, the block structure grid, and all the other infrastructure is handled by your framework. Throw the rest of the stuff away. There's a lot less writing. There's a lot more writing initially to write the framework, but a lot less writing after you have it working. And you get your parallelism, your modularity, and your portability for free, which is a huge plus. So this is kind of our Thorn architecture here, where you'll have your source code is one piece here, and that was that piece that I was talking about up here. You still have to say something about what the free parameters are in the param.ccl, what your interfaces are for invoking your module, and also the scheduling constraints. But all of this other stuff is kind of semi-automatically generated. Documentation, we used an early version of Deoxygen, but you should write real documentation. The make file stuff and the parameter files and test files are all automatically generated, and the wrapping for any of your source code is all automatically generated. And so it's kind of built up this ecosystem of plugins over time. So it used to be that it was just the central, your flesh here was the make system, error handling, schedule, and grid variables. But people have built all of these different driver modules. They've got remote steering interfaces, different interpolators and multi-grid implementations, and memory managers are all built up in a modular, interchangeable ecosystem here. So one of the first things you can get out of a fancy framework like this is that's a lot of fun is auto-tuning. And so this example shows that once you adopt this discipline of software engineering in a framework, these higher order things can emerge that were really unanticipated at the time that we wrote it. So it enables you to automate the tuning for parallel performance of the code without actually changing any of the solvers directly. You actually change data layouts, change boundary exchanges, all sorts of stuff. So normally people accuse abstractions that you see in frameworks of reducing performance, and this is actually shows how framework abstractions can enable performance tuning. So this was a Gordon Bell for I think it was 2000, maybe it was 2001. I can't remember which year. It was either 2000 or 2001. The idea here is that we had two SGI origin 2000s that were separated by continent. So we had one in Germany and one in the US. And it seemed like a crazy and stupid thing to do, but we used to do kind of gonzo stuff like that back then. The idea was that they have this big virtual supercomputer. First time we did it in 99 or 2000, the performance stunk. But then we learned a set of tricks to actually improve the performance, like using compression, communication avoiding stuff, like sending having more ghost cells and exchanging less often. And then we decided, well, which combination of those tuning ideas you should apply is kind of a runtime decision, and depends on your current grid size and situation. So what they did here is that they rewrote the AMR, the MPI unigrid driver, so that it would start with the standard number of ghost cells that we'd have in Cactus. It would automatically start adding additional layers of ghost cells to avoid communication or and batch it up into larger messages. So it would add 2 ghosts, it would see that performance improved. It would add 3 ghosts, and then it would see performance improve further. It would add 4 ghosts and say, that's enough. And then it would turn on compression. And so it would keep on trying different adaptations. And if they reduced performance, it would back off that adaptation. And if it improved performance, it would take that adaptation and then apply another layer of tuning to it. Yeah.
So in terms of the auto-tuning that's happening here, it sounds like you're just applying greedy search, essentially?
Yeah. It's greedy search, but it's being done in a way that, I mean, the key thing here for the auto-tuning adaptation here is that we're really trying all the different tricks that we know of for the communication optimizations. And those communication optimizations play out differently depending on the current networking conditions. So we made it a runtime optimization instead of a compile time optimization. Another important thing, though, is that when they wrote this MPI unigrid driver, no lines of source code in the solver had to change. Because of the discipline that was used in writing those modules, they were able to create an auto-tuning communication driver without requiring the physicist to change any of their code or the numerical analyst to change any of their code for the middle layer. So that was kind of cool.
Why did the efficiency peak and then drop again after every change?
So this was a timing anomaly is the best I could say. It would have to run multiple cycles for you to know whether or not it was the right thing to do. So yeah. So let's see here. This was, this is 2002. So this was the task farmer, and this was the bioinformatics demo. we'd have like Seaborg, which was our supercomputer, here would run a enormous, well, actually this one we'd set up as a black hole thing, but we use the same driver to do the bioinformatics. The idea here is that we used a grid framework to do remote spawning of computation. So on Seaborg, we ran the master simulation, but then you'd need to run analysis in some of the waveforms that were coming out from the big simulation. And so it would actually submit subjobs to smaller machines that were remotely located to perform additional analysis tasks. And also and so this could happen recursively, and then we had a web interface that we used to control the simulation and also to aggregate all of the results from these tasks that had been farmed out to perform analysis or other sub-computations for it. And so, yeah, that's right. This example was used to farm out Smith-Waterman for DNA sequence mapping. And we also had a generic web portal. Now they call them science gateways, but we had a generic web portal interface that would manage the distributed computations. Yeah, somebody had a question? No. We also, because the Cactus was introspective, we were able to bake in our own behind-the-scenes checkpoint restart mechanisms. So we had the usual, if there's an error, everybody stops and then you resubmit the job type interface. But we actually implemented a localized checkpointing interface where it would do a running log of the communication and the current state of memory while it was stepping forward. It would stash a copy of this running log in a neighboring processor. So if one of your CPUs failed, you could actually recover from the state that you stored in your neighboring processor and continue stepping forward instead of having to do a complete global checkpoint. It was all completely localized recovery. This is another migratory code example. When this was, we had a project with like Jack. I thought you were part of it too. Maybe it was like Andrew. It was called Grads. Was it Rice? So it's like it's like Ken Kennedy. Jack was there. Andrew Chen, and so this was like a migrating job example where it basically you'd be stepping forward in time. You'd be scavenging resources. You'd see your performance drop because other things start sharing the resource. So then it would checkpoint itself, and it would search for another machine, and then it would start itself up on another machine. We called this the Cactus worm, slightly before they had the worm incident, and then we stopped calling it the Cactus worm. We have hybrid communication. If you go to the Cactus web page, we wrote a web browser interface so that you can use your web browser to connect to a code while it's running and query it and see what it's doing and even steer it using the web interface. You can send, years ago you could send text messages to your code. It's been upgraded to have its own Twitter account now, but so you can chat with your code and you can actually type a text message saying, how's your convergence going? And it'll report its convergence rate and stuff like that. It's kind of cool. I had nothing to do with it, but I and lots of remote viz tools and stuff. So, in the real world, we have our numerical relativity. I already talked about a lot of this stuff, so I might kind of move forward here. So it's got a long history in numerical relativity. There's a CFD toolkit that has finite elements dwarf that's kind of coming online at LSU. And we're going to just completely switch gears here and move on to Chombo. Yeah, I think I'm going to do Petsy. I'll just say a few words about Chombo, and then we'll just move on. So Chombo is AMR, and AMR has lots of pretty pictures. So at minimum, we have to show Chombo's pretty pictures. The thing that's interesting with AMR is that in addition to the discipline used for the managing the communication and data layout, it adds a whole nother level of complexity because now you have these refined regions with block structured grids over areas of refinement. And so your control complexity is huge for this. Unless you have the discipline of a framework to organize and manage those computations, these codes would otherwise take years to write. Now that you have BoxLib and you have Chombo, you take advantage of the framework to orchestrate those computations, and you can focus on writing physics plugins, which are, again, written with the same kind of discipline we used for Cactus, but you take advantage of, basically Phil and, John Bell have baked their expertise on AMR and how to do efficient computations. They've baked it into their framework, so it does that behind your back. So we're going to skip through this. This is for your info. You can see this at your leisure. All of the cool things, cool tricks that you can do with AMR. And this is, by the way, if you use their discipline for writing the code, being able to resolve the complete data flow dependencies between different solvers and different levels of the AMR grid can be done analytically and static, at runtime very, very trivially. Whereas if you just wrote this in Fortran and you weren't adhering to the discipline required by the framework, this would be damn near impossible to do with straight Fortran code. So there's a layer above, taking advantage of that layer of semantics that's above the base language of Fortran makes all this analyzable by your driver, and the driver exploits this information to schedule things more efficiently than any human programmer could do by writing the code and following the textual order. All right. It scales. Scales a lot better than naive code. That basically says frameworks are better than writing hand-coded stuff. Everybody is afraid to give up hand coding, and this says that there's lots of cool things you can do with data layout, like using Morton ordering to improve your communication locality. And these are things that are out of band from the solvers that the programmer writes. So there's a lot of opportunities. All right, so PETSI. So PETSI is, another set of PD solvers on block structure grids, but it also includes a lot of dense and sparse linear algebra capabilities. And it has this kind of a stacked layer here. But I just wanted to point out that, it's the discipline for their layering here is very much built around that kind of three-layer cake that I showed earlier, where this outer wrapper here is, I'm targeting the mathematicians. How do I specify the mathematics of the problem and keep that isolated from the guts, the details of how I implemented the parallelism? So, you have these data objects here, and that's the same as the grid functions that we had in Cactus, which are these abstract objects, containers for data, but they have a very specific semantic meaning that is meaningful to the mathematicians, not just to the computer scientists. And then, you go to the next level down, which is the solver's level, which is how do I solve the problem? And so I have these layers of the stack here, which are my collection of solvers that take those data objects and I use them to solve the problem. And so, Krylov subspace methods, preconditioners, basically PETSI encodes at least a dozen different people's PhD theses, and that expertise is packed into this. And then the last thing is, how do I implement the parallel computation? And I do this, as a grid management interface and the low-level interfaces to MPI, MPIO, BLAS, and stuff. So it has exactly the same kind of isolation into three layers of abstraction that I was talking about earlier in the general discussion of frameworks. And lastly, something I thought was kind of cool is that they also have debugging and monitoring aids. This is kind of like all that extra stuff that we sprinkled around in Cactus, debugging thorns, performance profiling thorns. And so, again, you get this as a second order side effect of applying this discipline to solving the problems. So, so here's some of the stuff that, this is kind of the target space of computations that PETSI was designed to tackle. So you have nonlinear solvers, time steppers, Krylov subspace methods. It's got matrix arithmetic. And it has these base objects of vectors and distributed arrays and matrices to implement that. So these are kind of like their base data objects. You have, vectors are fundamental objects to store your fields for your right-hand side, solution vectors, et cetera, and the matrices, fundamental objects to store operators. The key thing to understand here is that when they say matrix, it's meaningful to your applied mathematician, and it provides interfaces for inserting things into these matrices in operations you can perform in the matrices and vectors that make sense in the domain applied mathematician's space. And they hide the details of how these things are laid out so that your performance programmers can actually do stuff behind the back of your applied mathematician. So like here's a simple example with generating a PETSI vector. I say vec create. So it creates this opaque vec object. And then I have the next layer down of this where I can say that it's a sequential vector, or it's an MPI vector, so it's in a distributed memory, or it's a shared memory vector. So you can annotate your vector by additional information that says something about the underlying parallel programming environment. If you're very disciplined in the way that you write your code, though, you hide this part because this is what your performance programmer is worried about. And this part up here is I just want to create a vector. I don't care how it's laid out. I don't care what's underneath. It's a vector, and I'm going to apply some operations to it. Now, one of the key operations I want to be able to do is say how large the vector is. So this is how you set the size of your vector. And you can let PETSI decide how it should partition that vector across your parallel computing elements with the PETSI decide. And then you can destroy your vector. So basic object-oriented type operations here. So this is examples from the processor layout. So this is like a typical initialize everything, you create a vector, set the sizes, set some other options that you want, and then you can perform a bunch of vector operations on it, and PETSI finalize. So instead of MPI init and MPI finalize, all the guts of what MPI needs to do are hidden from you, and you just initialize the framework and let it do its thing. So these are the typical set of operations that are applied to the vector in the vector objects. Very typical. And if that vector, the vector has metadata associated with it that tells the PETSI framework how it's distributed in memory. So you say vector scale or vector copy. It consults the metadata about said vector to find out how exactly it should go about performing that in a distributed parallel environment, and is able to carry that out without the applied mathematician getting into the guts and details of how to do the communication and all the other things. Similar for matrix, create a matrix, set the type, set the sizes, and destroy. And then you should have a bunch of, so there's a number of different matrix types to describe how it is laid out in the memory. So you might want to have your matrices be local objects, or you might want them to be partitioned global objects,
And those are all sparse, that's what it's mostly for.
Yeah, yes. Right.
But there's dense in every other kind.
There's dense in there too. I had a bunch of these slides that I had put on hide, and so you'll find in the presentation there's a lot more slides that I'm presenting here. And I was desperately trying to unhide a bunch of stuff, but we'll go with what actually is unhidden here. And so there's, as you know, with sparse matrix algebra, there's a lot of different choices for how to encode your array and encode the data, and PETSI supports almost all of them. So it makes what would be a whole bunch of loops and a whole bunch of code as simple as saying an annotation to my matrix, saying this is how I want you to encode my matrix. And so it's very flexible, very powerful to have such complicated things encoded into the, in a simple, apply this operation to the matrix. This is just a simple example of how it decides to do data layout for the matrix. Again, you can actually, if you're a performance programmer, you get to actually specify what the data layout is. If you're not the performance programmer, there's always the PETC decide option where you say, this is how large my global vector is, and I'm going to use MPI, but I'm going to let PETC decide how to lay this thing out. And that hands control over to the library and implicitly to your performance programmer to deal with those details. And then just like Cactus, it has a lot of viewer options. So once you've baked into your framework all of the metadata that describes these arrays, how they're laid out in memory, you can have an arbitrarily complicated PETC code, and you can plug in, you can just say, view this array, and if it's a matrix, it figures out the correct way to view that matrix as a matrix, and if it's a vector, it basically understands contextually how to draw the data objects that are contained inside the library, and also how to query, for the existence of those data objects in the library. So there's viewers, there's vector fields, different output formats. There's simple graphics created, X11 graphics. There's all sorts of little things that you can do to query and understand your data. So those are just standard viewers that they have available. Matrix market form, MATLAB viewer. And then the last thing here is implementing more complicated things like these Krylov subspace methods. It basically enables you to accelerate the convergence rate for some of your numerical schemes. There are a lot of things in the cookbook for preconditioning, and so having them again encoded in the library allows you to mix and match lots of different options here. And I think I'm running out of time, so I am going to, okay, so here's your control flow. So, you have your main routine here, but again, the interface is set up in PETC so that you just declare the existence of objects and what you want to apply to those objects, but you leave it to the solver to actually decide what's the right schedule, the best approach to actually achieving the solutions you decide. PETC is a little different than Cactus in that you can actually take control of Main if you want to. That's crucial when you want to use PETC as a library, but PETC as a framework, Main is kind of elevated outside of the part that describes the solver and such. I'm going to skip ahead. So this is a summary slide, and then we'll be done here. So computational science is increasingly carried out by large teams and impossibly complicated code bases. Frameworks are the software engineering practices to enable large, diverse teams to collaborate in the development of the code, but they also have the benefits of being modular and highly configurable and extensible. And then lastly, they hide all of the complexity and the details of parallel computation and data layout. And so isolating your applications layer from the solver layer and the low-level driver layer enables better reuse across application domains and better scalability for novel computing architectures as they come out. And that's it.
Shall we thank the speaker? I had one more PETC question. If you had to say which dwarfs it supported?
Sparse and dense linear algebra and some PDE.
So structured grids? Or?
Structured grids as well.
Okay.
And I'd say some structured grids. It's very specific. I mean, we used it for the BiCG stab for multi-grid stuff, so you could think of it as implicitly representing it as a matrix, but PETC is found in many linked to many block structured grid codes.
So you should all feel free, even though this is late in the semester, to think about using frameworks for your class project. It's hard to say everything you could possibly use in a class project at the beginning of the semester, so That's, but, you know, all of this is fair game.